Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 12, Gravitation, Video 5. Today's topic is Kepler's laws for planetary motion. The objectives are: know the laws that describe the motion of planets, understand total energy and angular momentum are conserved in planetary motion, be able to apply Kepler's laws to solve problems. Kepler's first law. Each planet moves in an elliptical orbit with the Sun at one focus. That means the distance sp plus s prime p has to be constant at all points on the curve. We treat both planet and the Sun as points. So there are a couple of vocabularies. First is major axis. Major axis is the longest dimension with half length of a. So the longest dimension from one side to the other side. The half length A is called the semi-major axis. So we use this A in our calculations. Another vocabulary is the distance of each focus from the center to ellipse is called EA. This EA is really E times A, where E is a dimensionless number between 0 and 1 is called eccentricity. So if E equals to 0, then EA would be 0. So the two focuses will become the center of the circle. So the shape of ellipse is becoming a circle. For Earth, that E is almost 0, it's 0.017. For Venus, it's even more circular, E equals to 0.007. The other vocabulary is perihelion. Perihelion is the point on the curve closest to the Sun. So here is a point called the perihelion. There is another corresponding point that's furthest from the Sun that is called aphelion. Kepler's second law says a line connecting the Sun to a given planet sweeps out equal area in equal time. So this is a line connecting from the Sun to the planet. This, for example, in 1 second over here, this area is the same as sweeping out over here in 1 second. So as you can see over here, when it's closer to the Sun, the area is bigger. And I mean, not area is bigger, the arc is longer because the focus is closer to the edge. On the other side, when it's further from the Sun, the arc is much shorter. So this has its implications. Since gravity is the only force acting on the planet, its total mechanical energy has to be conserved because gravity is conservative force. That means when a planet is near the Sun, it must have more kinetic energy. It has to go faster because the arc has to be longer and less potential energy. When the planet is away from the Sun, it has less kinetic energy and more potential energy. That means over here it has to move faster, over here has to move slower. Since FG and R lies along the same line, so here is FG pointing toward the Sun, R is also pointing toward the Sun, so the torque produced by gravity around the Sun has to be 0. Hence the angular momentum has to be conserved. That means V1 times R1 has to be equal to V2 times R2 because M is the same. So M canceled out. So both mechanical energy and angular momentum are conserved. Third law says the period of planets are proportional to the power of 1/2 of the semi-major axis length in their orbits. So this one is very similar. For a circle, this instead of A, we use R, but for ellipse, we use semi-major. In this equation, ms is the mass of the Sun, A is the semi-major axis. Take a look at this. This T does not depend on eccentricity E. That means an asteroid of elongated elliptical orbit with semi-major A will have the same period as a planet in a circular orbit of radius A. The key difference is that the asteroid moves at different speed at different points in its elliptical orbit, while the planet's speed is constant around its circular orbit. Let's take a look at this example. At what point in an elliptical orbit does a planet have greatest speed? So according to the second law, this line SP sweeps out the same area in the same time, so it has to go faster in perihelion, and slower at aphelion. So where is the greatest speed? At perihelion. Another example, an asteroid Pallas has an orbital period of 4.62 years and an orbital eccentricity of 0.233. Find the semi-major axis of its orbit. So we know the period, we know the mass. From that equation, we can find the semi-major. A equals to G ms t squared divided by 4 pi squared to the root of 1/3. So what do we know? We know ms is 1.99 times 10 to the 30. We also know capital gravitational constant. We also know the period. Remember, in these equations, t has to be in seconds, so we have to convert that in seconds. 4.62 years, and 1 year has 3.156 times 10 to the 7 seconds. By the way, this number is in the back of your textbook. Plug everything in, you'll have A equals 4.15 times 10 to the 11 meters. As you can see, this eccentricity has nothing to do with period, so it's not used to calculate A, not in this question. Another example, Comet Halley moves in an elongated elliptical orbit around the Sun. At perihelion, the comet is 8.75 times 10 to the 7 kilometers from the Sun. So this distance is 8.75 times 10 to the 7. At aphelion, it is 5.26 times 10 to the 9. So this distance from the Sun to the further point is 5.26 times 10 to the 9. Find the semi-major. Semi-major, so we know this distance, okay, from perihelion to the Sun. We also know from the Sun to aphelion. So we can add the two together, divide by 2. That will give us the semi-major. Eccentricity is, we can find EA if we know the semi-major. We use semi-major minus the distance between the perihelion and the Sun. We get EA. If we know EA and we know A, that's how we can find E. EA is E times A, which is A minus the distance from perihelion to the Sun. So E equals to this number divided by A, which is 0.967. So it's very elliptical. It's almost very flat. Next one, what is a period? The period has nothing to do with eccentricity. Period is 2 pi a to the power of 3 over 2 divided by square root of GMS. Plug everything in, you'll have t equals to 75.5 years. So that's how many cycles? That's a cycle for one round. That's a time for one round. So it takes 75 years for it to come back. Planet orbit around the center of mass. Since gravity is action-reaction force, so both planet and the Sun orbit around their center of mass. So Sun is not stationary. Sun actually is moving. Seems like the planet is revolving around the Sun, but it's not true. It's both Sun and the planet are moving around the center of mass of the two things. But because the Sun's mass is about 750 times the total mass of all planets combined, so the center of the mass of the solar system actually is within the dimensions of the Sun. It's not in the center of the Sun, obviously, but within the Sun. So it's really, really close to the Sun. Now let's take a look, check your understanding. So the orbit of Comet X has a semi-major axis that is 4 times larger than the semi-major axis of Comet Y. What is the ratio of orbital period? X to orbital period Y. So let's see the relationship. T is proportional to A to the 3 over 2. So Tx over Ty equals Ax over Ay to the power of 3 over 2. So it has, X has 4 times of the Y. So it's 4 to the power of 3 over 2, which is 8. The ratio of the orbit period X to Y is 8. That's it for today. Thanks for watching. See you next time.